Hey y'all, so for today's lesson, getting into chapter 6, I've got this video for you to help you sort of guide yourself through this since we can't have class this week. So chapter 6 is all about random variables. We're going to start talking about random variables today. Our goals is to figure out how to calculate probabilities using probability distributions, either discrete or continuous. We'll get to mostly discrete ones today. We're going to look at calculating the mean, also known as the expected value of a discrete random variable, and we'll be calculating and interpreting the standard deviation of a discrete random variable. So if that's what you're looking for, here we are. So to start us out, let's say we play a game. So I'm going to flip a coin 4 times. So I have this coin here, I'm going to flip it 4 times. If the coin lands on heads 3 or more times, then I win. If the coin lands on heads 2 times or less, then you win. So think about it for a second. Who is more likely to win? Maybe pause the video and see if you can figure it out. And then we're going to create a probability distribution to describe this game. So if you're thinking about this, if I'm going to flip a coin 4 times, there's essentially 16 different things that can happen. We can get heads 4 times in a row. We can get tails 4 times in a row. Right? So there's one way to get all tails, one way to get all heads. Okay? We can get 3 tails and 1 heads. There's 4 different ways to do that. Same thing with heads. There's 4 different ways to get 3 heads and a tails. And then finally, the most likely outcome is 2 of each. We know there's a 50-50 shot, so this is obviously the most likely. There's 6 out of 16 ways for that to happen. So what we're doing here is building a probability model. We're going to map out all the different possible outcomes and the probabilities for each. So a lot of times when we do a probability distribution, we use a simple table. So in this table, I'm going to have all the possible outcomes and the probabilities of each. 2, 3, 4, 5. Okay, so the first thing I'm going to do here is I'm going to define a new variable. I'm going to call this a random variable x. So x is going to represent the number of heads that are flipped out of 4. So x is our number of heads when we play this game. So the values for x, we could get 0 heads, 1, 2, 3, or 4 heads. So those are all the possible outcomes of x. And every one of those possible outcomes has an associated probability. We just looked at that. So the chance of getting 0 heads is 1 out of 16, and so on. So we can fill this in, and we've got a probability model. So we've seen these before. We can also call this a probability distribution because it tells us the values that our random variable can take. This is a random variable. We've defined this random variable x as the number of heads we get out of 4 tosses. So a probability distribution has a random variable and its possible outcomes, and we also show the probability that each one of those will happen. So back to our game, who's more likely to win? Well, if we look at this, I said that 3 or more heads, and I win. So that's a 5 out of 16 chance. Okay? If we wanted to apply some of our fancy probability notation to this, we could say, okay, what's the probability that I win? So Mr. Jaeger wins. Well, that's the probability that x is greater than or equal to 3. Right? I said that I win if I get 3 or 4 heads. So that's going to be 4 out of 16 plus 1 out of 16. Right? If we really wanted to be real picky with our notation, this is equal to x equals 3 plus probability that x equals 4. Just to be really, really clear with our work here, we can show every single step. So you can see the probability that I'm going to win this is 5 out of 16, which means the probability that I don't win, aka I lose, is going to be the complement to that, 1 minus 5 out of 16, which is of course 11 out of 16. So it looks like you, in this scenario, have a better chance of winning because there's more ways to get 2 or less heads, than there are to get 3 or more. So that's pretty straightforward. Let's quickly just wrap up those definitions we just learned, and then we'll talk about a way to make this game a little more interesting. So we said a random variable takes numerical values that describe the possible outcomes of some chance process. So our variable here is the number of heads that are going to be flipped when we play this game, and it's a random variable because it could be 0, could be 1, 2, 3, or 4. A probability distribution displays those possible random outcomes along with the probability of each one happening. So in our coin flip game, this is an example of a discrete random variable. Discrete means we have a fixed set of possible outcomes. There's only 5 possible outcomes here, 0, 1, 2, 3, or 4. And there's no gaps in between. We can get 2 heads, or we can get 3 heads. We can't get 2.1 heads, right? Can't get any values in between. So that's what discrete means. We'll also look at continuous variables later on. Okay, so the next part says, let's make our game a little more interesting here. So we're going to do the same game, 4 flips, 3 or more I win, 2 or less you win. And we've already found out that you have a better shot of winning, 11 out of 16 versus 5 out of 16. So let's make it interesting. Let's say that if I win, you have to pay me $100. And if you win, then you're going to win $75. So with these new rules, we're going to create a random variable to represent the possible amounts of money you could win or lose. And then we're going to create a probability distribution to show off that new random variable. And then we're going to ask the question, let's say we could play this as many times as you want. Should you play this game? And we've already found out that you have a better chance of winning. But if we're adding this money involved, you lose more than you stand to win. So you lose $100, you only gain 75. So you have better chances of winning. We gotta ask ourselves, is it worth it? Because we win more often, but we win less money than we lose. So we gotta figure out if it's worth it or not. Let me escape, please. Okay, so let's take a look if we can create a random variable to represent the possible amount of money that we could win or lose. So we're going to use what we already know to create a new random variable. And we've already used x here. So this one I'm going to call y. So y is the amount of money gained or lost. Okay, so we play the game, and let's think about what can happen. So first we want to figure out what are the possible values of y. So we said that if you win the game, you win 75 bucks. Okay, good deal. If you lose the game, you lose 100 bucks. So the possible outcomes for y equaling your amount of money you gain or lose, you either win 75 or you lose 100. Each one of those things has an associated probability. So we already found these out earlier. The probability that you win and gain $75 is 11 out of 16. Notice that's the same thing as the probability of me not winning, is you winning. And the probability of you losing, aka me winning, was 5 out of 16. So another probability distribution here, this time describing how much money we could gain or win. There's 11 out of 16 chance that you gain 75 bucks, and there's a 5 out of 16 chance that you lose 100. Okay, so the question still stands, should you play or not? We can see there's a better chance of winning, but you win less money. So how can we weigh those chances? Well, the idea is something called expected value. So you've probably calculated an expected value before, you just didn't know it. This is the same thing as a weighted average, essentially. The expected value is a way for calculating the mean of a discrete random variable. So we can figure out what is the average, in our case, y. What's the average money you win or lose when you play this game? We can calculate this by taking each outcome value and then multiplying it by its probability. Then we just add those together. This is something that's provided on your formula sheet, and it looks much more complicated than it is. So this is what you'll see on the formula sheet in that little table. It'll say to calculate the mean of a discrete random variable. Mu means mean, so mean of the random variable x is equal to e of x. So that's just another way to say expected value, just another notation. E of x and mu of x, those mean the same thing, the average outcome. And finally, to actually solve this, we would take each outcome value, each x, multiply it times the probability of that x happening, and then add up all those products. Okay, so let's try that. And again, the formula makes it seem much more complicated than it actually is. So the mean of y here, because that's the name of our random variable y. So the mean of y, which we could also call the expected value of y, just different notation for the same idea. We'll call it expected value. But just remember, this is the mean. Well, we would take each possible outcome, so $75, and multiply it by its probability. Okay, we're also going to do that for the other possible outcome, which is negative $100. And we'll multiply that by its probability. Okay, so again, this is just a weighted average. If you wanted to calculate your grade in this class, for example, you could do this, right? Quizzes and tests take up, I think, 60% of your grade. Labs and homeworks each take up 20% of your grade. So you can take your test average, multiply by 0.6, take your homework average, multiply by 0.2, take your lab average, multiply by 0.2, add those all together, and you get the mean, right? The actual weighted average or expected value. Of course, that's not a random variable, but it's calculated the same way. Okay, so let's take a look. I hope your grades aren't random. So we've got that value plus negative 100 times 5 over 16. And we get the expected value, 20.3125. Okay, so how do we interpret this expected value? Well, we'd say, okay, if I played this game over and over and over again, each time I play, I expect to win on average about $20.31. And by I mean you, right? We can see that we're looking at the amount of money you gain or lose. So it looks like you're going to gain about $20 every time you play this game. Now, I should say, if I just told you, you can play this game one time, would you play? Even though you have a better chance of winning, that's gambling, right? We don't have a guaranteed chance to win, right? There's a pretty good chance that you're going to lose $100. So playing one time by no means guarantees that you're going to win, even though the expected value is a positive number. You're more likely to win than lose. However, there is always a chance to lose here. So that would be gambling, and of course, we don't condone gambling here. However, if you could play this game as many times as you wanted, it's no longer gambling, it's statistics. If you could play this, sit here and play it 1,000 or 10,000 times, you make $20 on average. So you should absolutely do it. So if we look at the formula sheet, we can see right here we have the expected value, the mean. The mean is we take the possible outcomes, multiply probabilities, and add those up. We can also calculate the standard deviation of a discrete random variable. So there's a little bit of a more complicated formula for that. So I'm going to show you how we would calculate this, and then we're probably never ever going to do this by hand again. There we go. So I'm going to show you how to do it once, and then I'll show you how to do it in the calculator, which will be super useful. Okay, so to calculate the standard deviation of a discrete random variable, so the standard deviation of y, so standard deviation, sorry about that, standard deviation of y, well, we're going to take the square root of the variance. So the variance is where we take each possible value and we subtract the mean of our random variable, which we just found. We're going to square that, and then we're going to multiply times the probability of that outcome happening. And this looks pretty scary, right? This is a big ugly formula, but it's not too bad. But again, not very fun to do by hand, even with only a couple values. So we only have two possible values. So we would take each one of those, 75 minus the mean, which is 20.3125. We just calculated that here, right? Remember that expected value is the mean of y. All right, we're going to square that, square the deviation, multiply by the probability of 75 happening. So that was 11 out of 16. Okay, remember this means sum. So we're going to also do this for the other possible outcome and add that together. All right, so I've already done this. We went through, we subtract this and squared it, multiplied by the probability and all that business. And let me see what I got here. I got 81.115. Trust me on this, if you do this carefully, you'll get the same thing. But I never ever do this by hand. There's an easy way to do this in the calculator. So I'm going to show you here, and then if you need to do this, you can come back and watch the video again. So we're going to use our old pal 1var stats. Even though this is a more complicated problem, we're looking for really simple one variable statistics, the mean and the standard deviation. We've been doing that all year. So let's first go into our lists, and we're going to enter our data into list 1 and list 2. So you can see what I've done here. I put list 1 is the possible values of y, either positive 75 or negative 100, two possible things we can win. Okay, and then I've got the probabilities of each in here. So you can see this is a decimal, but I just typed in 11/16 and it changed it to a decimal for me. Okay, so that's what those are. Okay, so once we have this in list 1 and list 2 for the probabilities, we're going to go over to 1var stats. We've used this before, but last time we used it, we left that frequency list blank. So what that's talking about, frequency list, is how often each of these outcomes happen, right? In other words, the probability. So I'm going to say list 2, right, where I put those probabilities, is going to be my frequency list. Click on calculate. And look what we get. We get x bar, aka the mean, is 20.3125, and the standard deviation is 81.111115, which is what we get if we do all this garbage. Now again, for standard deviation, I never recommend doing this by hand. Expected values, not too hard to deal with, but this gets messy, and this is with only 2 possible outcomes, right? If we had a probability distribution with 10 possible outcomes, no one wants to do that, right? No one wants to calculate that by hand. It's possible, and you should understand how these things are calculated, but again, let your calculator help you out here. Okay, so what we did here is we played this game. We had 4 coin flips, and we said, if I get 3 or more, then I win. Okay, we figured out that I was much less likely to win the game, so we made it more interesting by adding some money here. So you win, you get 75 bucks, but if you lose more, you lose 100. And we still found out that it was still advantageous to play this game, even though you stood to lose more than you gained. Now, this whole experiment is working under a certain assumption, right? You should play this game for sure. You make $20 every time you play. If you could play this all day, it's not gambling, right? If you could play this all day, you're guaranteed to, well, maybe not guaranteed, but on average, you'll definitely win more than you'll lose. Now, we did make an assumption that this coin would land on heads 50% of the time, and maybe it wasn't fair to make that assumption. Now, this is a normal coin. This is a Dwight D. Eisenhower silver dollar. It was rigorously inspected by my teaching assistant, and well, she's not really the most scientific mind there is, but she did her best. But it is a normal coin. It's the biggest coin I had, so you could see heads and tails easily. That's actually a really cool coin. Hang on a second, I'm gonna nerd out here. On the back is an eagle landing on the moon. You can see the Earth in the background there. Really neat coin. But I cheated. Okay, so I picked the biggest coin I could find, not only so that you could see it better on camera, but also so that I could control my flip. So I wondered if I could do this, if I could take a normal coin and see if I could perfect the coin flip. So here you see me doing a sample of 100 coin flips, and I'm going to try to get as many heads as I can. Now, some rules: I can't do something lame like just barely pick it up. I actually had to flip every coin up in the air at least a foot or so, and had to turn over. It had to be a flip. And I did my best to get as many heads as possible, trying to control that flip. So I did this, like I said, 100 times. You can see me doing every single one of those. I dropped a couple. The ones I dropped I didn't count. So I had to land in my hand, had to go up in the air. And through all this, I got, once I counted up, 72 heads out of 100. So my probability was 72 out of 100, which obviously is higher than 50%. But is it so much higher that I wasn't just getting lucky? Right? We know that if we flip a coin 100 times, we're not going to get exactly 50 heads every time. When we take a sample, we have natural variance, right? Sometimes we'll get a little more than 50% or a little less. So how rare would it be to flip a coin, a fair coin, 100 times and get 72% heads? That's pretty far from 50%. So because flipping a coin all day is not worth my time, what I'm going to do here is use some technology to repeat this sampling process that I just did over and over and over again. And the computer is going to assume that this is a fair coin, that we have an equal chance of getting heads and tails. And I'm going to do 100,000 trials, so flipping a coin 100 times, seeing how many heads we had. I'm going to do that same process 100,000 times, and then we'll take a look at the plot. Let me take this off real quick. All right. Hang on, gotta call that library first. There we go. Okay, so here are the results. So we have a histogram of all the proportions I got in 100,000 trials. So you can see that most of the time we got about 50% heads. All right, so most of our data is right around 50%. Right, this does kind of look familiar. So you'll notice a big chunk of our data is very close to 50%. And I've drawn a line over here at 72%, which is what I got, right, 0.72. In these 100,000 trials, 3 times we got more than 72 heads. So the probability that a fair coin would give you 72 heads or more is about 0.00003. It's extremely rare, which gives us a lot of evidence that I actually can control this coin. Heads, 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 tails. All right, I have a certain degree of control, especially when I'm using this big old honkin' coin that's pretty easy to manipulate. So over the next several classes, we'll be talking about sampling distributions, looking at all the possible samples that we could get given some random chance. Because although we know that a coin is supposed to give us 50% heads and tails, there's some variance. We get more or less when we actually carry out an experiment. But there's a limit, right? We would never get, or very, very, very rarely get 10 out of 100 heads, right? That's so far away from 50%. It's just not statistically possible. So understanding these sampling distributions and being able to calculate the mean and the variance of those is going to be something we're going to dig into really deep. So we're going to come back to this idea. And again, here we're just dealing with a discrete distribution, probability distribution. But you might notice this looks really similar to a continuous distribution that we have already learned before. There's the normal distribution drawn on top of our data. And you can see it matches really well. It's not perfect, of course, because it's not continuous, but pretty much every bar follows that shape of the normal distribution really, really closely. Now, this isn't a normal distribution, it's a binomial distribution, technically, which we're going to talk about in this chapter. But when the sample gets big enough, those start to become kind of the same thing.